Um, like I want to make sure I'm not repeating the stuff that you guys did in Mr. Van's class, but also making sure that when I hand off you guys to BC, or some of you guys might do AB. If you do AB next year, by the way, that's gonna be a breeze the first 2 or 3 months because a lot of stuff we've done, you guys have seen already. But majority of you guys are doing BC, so you'll be expected to do sequences and series. And even if you're doing AB next year in college or whatever, you're gonna have to do some sort of probably advanced calculus class that will involve this stuff. So there's all good stuff to get some exposure to it now. So we're going to look at sequences from a calculus perspective. Uh, Obviously, some of these essential questions you guys we have answered, like what is an infinite sequence in series? We've talked about that, right? Like a geometric sequence that's infinite goes on forever, and it converges if the ratio is between -1 and 1. And that's going to be a big thing we're going to talk about in this scene about convergence and divergence. So when is infinite series or sequence converge or diverge? And by the way, series is when you're adding up the terms, just so you know. That's what a series is. A sequence is just a list of terms, just so you're aware of that as well. So yeah, we're gonna have that discussion. So the introduction. So again, an infinite sequence, an infinite order list. A list of numbers usually having some kind of pattern. An infinite series is the formal sum of an infinite sequence. So just it sounds kind of the same, series and sequence, but sequence is a list, series is the actual sum. One way to view any infinite series is an improper integral of the associated sequence. Don't worry about that. We have not talked about integrals, so that's a little crazy. The notation of a series can be generalized further by multiplying each term in a sequence by a power of a variable x and form the associated series. So like, like it's like R, right? Like you have the initial term a sub 0, a sub 1 x, a sub 2 x squared, and so forth, right? This is called a power series because you're raising x to some power. To understand a power series, we must first study real valued sequences in series, which we'll do. This approach will divide our series used into two. The first will focus on real values infinite series, and our second will focus on more general infinite series called power series. So these are all things just to get familiar with, just the terminology, the notation, all that fun stuff. So over here, she kind of put together a definition of a sequence. A sequence is a list of numbers written in explicit order, where numbers are separated by commas. For example, in the infinite sequence, a sub 1, a sub 2, a sub 3, comma, dot, 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 a sub n, and so forth. A sub 1's first term, a sub 2's second term, and so forth. And obviously, these terms are the terms of the sequence. A sub n is the nth term. A sequence can be finite or infinite, depending on how we define it. Obviously, we're going to focus on infinite sequences, right? There's a little graph there. We can just marvel at it a little bit, move on. All right, so like example 1, for example. And some of these are kind of already worked out. So these should go by pretty fast. Find the 100th term of the sequence. Okay, so you guys should be pretty comfortable with that, right? Just plug in 100 and you're good, right? It's not that hard. Obviously, if you raise a negative number to an even exponent, it stays positive, or becomes positive, and the bottom becomes that. So that's fine. And we call this defining the term explicitly because you're going directly to it. Being explicit means being very direct, right? So because the form for a sub n is defined in terms of n, in other words, we can find the nth term by simply plugging in value of n or n minus 1 or whatever into the expression. There are a variety of rules by which we can construct sequences, but 2 particular types of sequences are dominant in mathematical applications. Obviously, arithmetic we've talked about already, common difference. Geometry we talked about, common quotient or ratio. So just identifying, like part A, I think it's pretty obvious. That's arithmetic, right? And what are you adding to repeatedly? B is pretty obvious. What are you multiplying by repeatedly? Then 1/3, right? And it's alternating as well because the signs are changing. Sometimes we call it alternating sequence. Now, we're going to shift our attention to limits. And this is the calculus part that plays a role here, right? So we're going to find the limit of a sequence and convergence divergence of that. So we're going to determine that. So consider the following sequence 1, 2, 3, 4, 5, pretty obvious. The explicit formula is a sub n equals n, right? And if you were to take the limit as n approaches infinity of that expression, of course that doesn't convert. But if I take the limit of n approaches infinity of n, what would you just get? Infinity, right? So that so that's the problem. Since the terms are getting larger and larger, it diverges, right? And by the way, for a sequence, we're not adding up anything. We're just looking at what the nth term could be. Can the nth term converge? That's what we're talking about. Will the nth term converge? Not the sum. We're not adding anything today. We're just looking at sequences. What's the numbers? So definition limit of a sequence. We say the sequence a sub n converges to a limit L if and only if L is a finite number. If it doesn't, we say it diverges. Don't necessarily say it does not exist. We use the word diverge instead. If the terms increase without bound, we also say it diverges, but to infinity, right? So let's look at these three examples. I think it's pretty obvious this is a constant function. Pretty obvious this is an exponential function. And I'm going to call this an alternating function. Why do I think I'll call it alternating? Yeah. So if I list the first few terms, 4, 4, 4, dot, 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 2, 4, 8, dot, dot, dot. And remember, starting with n equals 1, unless you're told otherwise. And here, -1, 1, -1, 1, dot, dot, dot. So every odd term is -1. Even every even term is +1. Okay. So this is the kind of key idea here. If we know for certain what the nth term will be, or what the last term. Okay, so in pink, if we know for certain what the last term will be in our sequence, then sequence converges to that value. Otherwise, it diverges. That's the essence of this example, right? So for a sub n equals 4, it goes on forever. Do I know what the last term is? I do. What is it? 4. So it converges. So 100% I know that, right? That converges. Now here, 2 to 10. Do I know that converges to? Nope. This is diverges. And it diverges to infinity. Now here, there is some predictability here. Every odd term is -1, every even term is 1. But do I know what the last term is? No. And you can say diverges. You don't know what diverges to. You could say alternates. If you want to be a little more clear, alternates between -1 and 1. Right? It's going back and forth. Okay. Questions so far? No? So again, we're taking what we have already done with sequences and series, and you guys have now become better at it, right? So we're just now looking at it through more of a calculus lens. Okay, moving on. Yeah, cool. Okay, example 3. Now for each infinite sequence below, determine whether it converges or diverges. Assume you start with n equals 1, right? So you find the limit as n approaches infinity. So from a more formal standpoint, we're going to say this, the limit as n approaches infinity of the expression. Actually, I should have used that notation the previous page, but it's okay. I should have, but that's all right. But anyhow, we're using limit notation here. So what do you think is going to happen? It's going to go towards 0. And that's because when you have a rational function, You can access the loaded dividers too if you want. Let's want to be antisocial because rational functions approach zero when the denominator has a higher degree than numerator. And so, yeah, it converges. Yeah, we don't care about the sum. We're just trying to find the last term will ultimately go towards, even though it's not exactly zero. I mean, like, it could be like a super tiny number, but we can say it converges. We can say because it's the limit situation. Now let's look at this next one here. This is involving a factorial. Factorials are kind of a big deal in AP Calculus PC in the series and sequence unit. So the limit is 1 over n factorial. Well, let's think about what's happening. It's kind of a weird situation. You put 0 factorial is 1 because I guess you're not multiplying anything, so you assume it's 1. The 1 factorial is 1 as well. So you have 1 factorial is, or a sub 1 is 1. What's a sub 2? 1/2, right? A sub 3? A sub 4? So I probably gather this, what is this approaching? 0, yeah. So it converges again.
How is 0 factorial 1?
I think it comes from, let me think about this one. I thought this before. See, your goal for factorial is to multiply down to 1, right? Oh, now I got it. It comes from a probability permutation perspective. So, for example, let's just look at I'm gonna leave that there because you're gonna make it too complicated. Well, 4 people, okay? So we got four students here, right? So I want to rearrange you guys, right? Like, okay, I don't want Marie to sit here and Sophie to sit there and Anna sit there and blah blah blah, whatever, right? That's 4 factorial ways, right? If you were to count it, I have 4 options put in this chair, 3 options put in this chair, 2 options there, 1 there. So 4 times 3 times 2 times 1 is 24. There's 24 permutations, 24 ways I could rearrange all 4 of you guys, right? Now, let's say Anna's not here, so it's just you 3, right? So how many ways can I rearrange Sophia, Maria, and Laura, right? How many times can I do that, right? Well, if I think about it, that's 6 ways, right? So I could do either Sophia, Maria, Laura, or Sophia, Laura, Marie, or kind of reverse it. It's 3 times 2 times 1, so it's 3 factorial. So now it's just you 2, right? So 2 ways. It's where you are, or you swap, right? Now 1 factorial. Okay, so Sophia's here, right? Just 1 way that could happen. Now, what if there's like this room's totally empty? How many ways can I fill up the empty chairs? Because they say empty, right? That's just what it is. Or say you order say you go buy a pizza, right? Now that's dealing more with combinations because order shouldn't matter about how many toppings you put. But what if you have like 4 toppings to choose from? How many different pizzas can you make? You can make 24. And you choose all 4 toppings. And let's see. Actually, I'm going to take it back. Let me. It does get a little confusing, but because order doesn't matter. But let's say you did care about the order which the toppings were put on your pizza, right? So there's 4 toppings you put on pizza. And you did care which top, like the layers, right? Let's say you care about that, like just putting like a bunch of mushrooms, a bunch of olives on top, and a bunch of pepperoni, a bunch of like bell peppers, whatever. There's 24 ways that could happen. But what if you decide not to put any toppings? That's 1 way. You just have a cheese pizza. So that's the reason why it's not really mathematical. It's more just a permutation thing. Like there's 1 way you could do nothing. Just don't do it. Just don't do anything. So that's the reason why. That helps. Okay, properties. Just remember we had limit properties back in the day, like earlier this semester. So given a sequence, and let's say the limit of one function as x approaches infinity is L, or the sequence, whatever you want to call it, it's the same thing, because a sub n is a function, right? So if you add the two sequences, if you take the limit of a sum of sequences, it's the limit of each sequence individually, added up or subtracted. If you have a constant, pull the constant out. If you multiply, you can actually multiply. If you divide, you can divide them. If you raise to the power, you can raise to the power. And remember we had squeeze theorem back in the day, so that could still apply. I'm not sure if we'll necessarily go down that path again. And absolute value, if you have absolute value something, then the sequence will be zero as well. It's kind of like ones that oscillate. You might remember we had sine x over x, which actually, Lucas, you bring up a good idea. I think we should probably start reviewing for the final pretty soon because there's a lot of stuff to be done. The more I think about it, I know you got APs, but maybe I could start incorporating some older stuff in this unit. Yeah. No, you bring up a good point though. But let's say I took the limit of this as x approaches infinity. Remember the graph looked kind of like this? And it oscillated. But the thing is, I know this is with absolute value, but of course that's going to be zero, right? So anyhow, some other things to keep in mind. If you have a constant, will that limit always exist for the sequence? Yeah. So it converges for all n values. That's because you have a constant function. Okay, this one's kind of interesting. If you have an exponential function, how does it converge? Converges when that happens. Oh, sorry, I meant to say A. That was dumb. So we know this. And you do talk about geosequences often in Precalculus BC on the series unit. This one is when you have a rational function. This will converge when your exponent is larger than what value? Zero, as long as it's positive. Yep. Now, the one thing that will be interesting when we talk about series, this series, when you add up all the terms, it actually will converge when p is bigger than 1. That's called a p series. We'll talk about that later in this unit. But this is what we call a rational function, right? And basically, that's what's a good example of that? Like that would be like a sub n equals 2 over n raised to like say the 0.1 power. Because ultimately the last term is going to be super tiny, right? It's getting closer to zero. We know this. If you have n go towards infinity. Because what you're doing in each of these cases, you're taking the limit as n approaches what? Infinity, yeah, totally. And in here, this diverges for all n values. So alternating sequence. So that's kind of just some common ones.
Orbits.
Cool. Okay. -1. What do you mean? Oh, you mean n?
No, so when -1 is your base, this will never converge. Sequence will never converge because I don't know what the last term is.
But like,
Oh, I see it. The base would be oh yes, correct. because what happens, yeah, actually, it's a great observation you made. Yeah,
That's actually really good because we do talk about that. Yeah, what if I have -2 raised to the n power? That's the same thing as saying this. You're allowed to break it off that way, 100%, because what's happening on the inside of the parentheses, you have this, and then you could distribute the exponents. And so what's happening? You got 2 to the n, which diverges anyway.
But you have alternating feature, right? And so
sometimes we have to kind of pull that out. Sometimes we got to do that. Yeah, it would still be the same, 100%. Yeah. All right. So, trying to think the best way to approach this one here. Let's take the limit first. There's a more advanced approach, but I don't think I can really talk about that with you guys because we're not ready to have that discussion. So I'm gonna have to kind of just take a more rudimentary approach to this one.
So I could just take a look at each part individually. You're allowed to do that. We can talk about one properties and take one of the numerator, the denominator, and find what's going on. Of course, n is infinity and 2 to the n's of course, right? So
yeah, it just sucks because there's an analytical approach, but I can't teach it to you guys right now because has anyone ever heard of I'm not sure some of you guys get ahead and do your own stuff, but has anyone heard of a rule called L'Hopital's rule? Or heard that?
Wait, is it like if the denominator derivative? Or is that something to do with like the limits, the derivative of the
It's with limits, and maybe I might teach it to you guys. I'll talk to Ms. York if she's okay if I teach you guys next week. So remember we did limits, right? Of like all these weird things. There's all this like trig stuff we had. You had to break it down. There's a rule that states that if you take the limit of something and you get 0 over 0, infinity, infinity, you could actually take the derivative of both top and bottom. And once you do derivative of both top and bottom, whatever, I'll give you a good example. Maybe I could teach you guys right now. Maybe you guys can handle it. What if I had the limit of this, x plus 1 over x squared minus 5? I know what this is going to be. What's that going to be? If I take x, it's going to be 0, right? Because the bottom has a higher degree than the top. We know that. But here's what you could do analytically. Take the derivative of both top and bottom. What's the derivative of the top? What's the derivative of the bottom? Now it becomes more obvious. That's 0, right? Here's another one. What if I have something like this here? Okay,
we've seen this before, right? If you plug in 1 right now, what do you get? 0, 0. That's a problem, right?
Totally, that's a problem. Okay. So what techniques did we do back in the day a few months ago? Yeah, we you don't have to write this down, but we factor this, right? And what happens after you factor it? That went away, and what are you stuck with? 1 over that junk, right? And you plug 1 and you get 1/2. Fine. What if I took the derivative? Because now you guys know about derivatives, right? What if I took the derivative of this? What do I get? 1 over. And now let me kind of take my limit. You get 1/2, right? So this is called, and some people kind of call it Le Hospital, but it's French. The S is silent. L'Hopital. L'Hopital's rule. So it's your
hospital.
L hospital, exactly. You're allowed to do this when the limit results in 0, 0, infinity, infinity. So in this case, I do have infinity, infinity, right? I do have that here. I do have that. So what I could do instead, and actually, you know what? I think we should talk about this because you get this is the calculus way of think about it, right? Let's talk about it. I'm going to take the limit as n approaches infinity. What's the derivative of n? 1, right? And you guys remember the derivative of exponential functions? We talked about this. Times ln 2. Yep. Now, if I plug in infinity, what does all that become? 0. Yeah. So you know what the heck? Good. We talked about this. I'm glad. We should. So yeah. So that's a rule called L'Hopital's rule. You're allowed to do this for limits. So even though both top and bottom are getting both larger, here's the thing. Why did this converge? Please. Right. Yes. It dominates. Yes, it's called dominance. Yes, that's it. So what happens at 2 to the n, and some people will do this. These are double greater than symbol because it's that much greater. 2 to the n is greater for large n because 2 to the n dominates. This is the dominant term. Because exponential functions increase way more quickly than n does. Think from a graphical perspective. What's 2 to the n? That's exponential. That's linear. Which one is steeper from a slope perspective? Exponential, 100%, right? We know that. So you can think of it that way too. Yeah. Yep. Okay, that's good. I think we analyzed that to death. So you guys should be okay with that. So if you want to use this new rule, go for it. 100%. I'm totally cool with that. I'll just let Ms. York know I talked to you guys. She'll be fine with it. I don't think she'll be all hurt. So anyway, L'Hopital's rule. What's going on there?
It's only for 0.
It's only when we have 0, 0, infinity. So when we have an indeterminate form, when something's indeterminate, like means you can't determine what the outcome is. Because 0 is 0, I don't know what 0 0 is. Because anything times 0 is 0. So 0 is 0 could equal any number. I don't know. So that's what we call indeterminate.
Like 1 over 0.
That's undefined because 1 over 0, I got no clue. How am I going to multiply something by 0 and make it 1? That's why we always say it's undefined. We have 0 on the bottom and a non-zero number up top. But when we have 0 over 0, I don't know. We don't.
They can't use the law.
Nope. It's got to be 0, 0 or infinity. Yeah. Okay. Same thing here. Limits n approach infinity of sine n over n. Now, I know what's going to happen here. What do you guys expect this to be? Probably going to be 0, right? Yeah, it's probably going to be 0. So the last one converge, A converge. This is probably going to be 0. Just by inspection, because the range of sine is from -1 to 1, and the bottom increases without bound. So of course the bottom is higher than the top all the time. Yeah, I mean all the time, but as n approaches infinity. So I expect this to be 0. But in order to prove it, because this will be infinity, and this is from -1 to 1, right? But to prove it, you guys remember what we do? Remember this guy? Came back. Remember me? Squeeze theorem. Okay. So what are we going to do? Let's compare this is true, right? What's the limit as n approaches infinity of -1 over n?
0.
And what's the limit as n approaches infinity of 1 over n?
Yeah.
So we make our statement. due to squeeze theorem. Sine n over n must equal 0. Sorry, limit as n approaches infinity must equal 0.
Wait, for this paper, it's because it's between the three dots.
Correct.
Correct. Because why do we call it squeeze? Because 1 over n is this.
Okay.
Negative 1 over n is this, right? And both are going towards 0, right? And then the time over n, does this, right? It's sandwiched in between.
So those are called sandwich theorem for that reason as well. That's what's happening, right? Okay, hopefully that makes sense for that one. Okay, and lastly, okay. One thing you're allowed to do here when you take the limit of a rational expression, you can take the absolute value. We saw that earlier. You can take the absolute value of the whole thing. Because we saw that if the absolute value approaches 0, then the sequence itself does approach 0 as well. So it's the same thing as saying this. So this definitely has a very good Precalculus BC flavor to it, because you do quite a bit of this in Precalculus BC. Okay. Well, if you have negative 1 raised to the n, what's the absolute value of that going to be? Just 1, right? And if n squared plus 2, is that ever negative? No. And because the bottom is a higher degree than the top, you have 1 over infinity, right? What's that going to be? So yes, that also converges as well.
Oh, so we saw a few things, a few techniques. We have tall rule, which you guys learn now. That's cool.
We did squeeze theorem, right? Brought that back. And then, of course, we did, some sort of, property of the absolute value. Okay, good. Yeah, you can, but it just gets wonky with the negative alternating series, because sometimes that just throws us for a loop. So if we could just sort of remedy that.
Okay.
That's the whole point, just to remedy that. That's all. Okay. So homework is included in your packet. So we still have like another 20-ish. I didn't put the schedule on the board. Great. Homework's right here. Yeah, you guys did the answer key as well. It's handwritten because I think Ms. York had to make this on the fly last year. So 10 problems. The answer's on the next page. 1 and 2, just listen to the first 5 terms of the sequence. 3 through 10, you determine if it converges, and you have all these different skills you can use now. Now you can use the Hull's rule if you like, if you feel so feel so inclined. You can do that. And there's some other ways this could be done as well. Yeah. So anyhow, give this a go. Excuse me.